Today we want to talk about integrating rational functions. So this is I usually do this after we do trigonometric substitution because the basis for this is going to be a trigonometric substitution. In particular, it's going to be one that we already know. So let's begin. Recall that the derivative of arctangent x, that's the tangent inverse of x, is 1 over 1 plus x squared. And so what this means is that if we integrate 1 over 1 plus x squared, we get arctangent of x. Plus c. Don't want to forget that. We'll lose billions of points. So the integral of 1 over 1 plus x squared is arctangent x plus c. Other things that we know. We know that the integral of 1 over x dx is natural log of absolute value of x plus c. And by substitution, if we have the integral of just a generic linear function, b plus mx dx, we have a natural log of whatever the linear is, but since there's a coefficient of x, we'll have a 1 over m factor. So mx plus b is just a generic linear term. When we integrate the integral of 1 over a linear term will be the natural log of the absolute value of that linear term. These are the important facts that we have in evidence. These are the things that we already know. What we're going after here, is we're going to build a base of rational functions that we can integrate. And then we're going to take our whatever rational function we're given and make it look like a bunch of these. Oh, I forgot one. There is another one that we need to deal with. So we've got 1 over a linear function. We've got a constant over an x squared function. I forgot the one in the middle, a linear over an x squared function. So if we have the integral of x over 1 plus x squared dx, this is a substitution problem where w equals 1 plus x squared. So we're going to have a 1/2 natural log of 1 plus x squared plus c. So we can get there by substitution. So on this last one, we're just doing a substitution. W equals 1 plus x squared, so that dw is 2x dx, so that a 1/2 dw is x dx. So the x dx is 1/2 dw, and that's where the 1/2 comes from. These three integrals are the basis for integrating rational functions. This is what we do with our denominators. So these three integrals form the basis for integrating rational functions. These three integrals are going to be the basis for integrating rational functions. The integral of 1 over x, 1 plus x squared is arctangent. The integral of 1 over b plus mx is 1 over m natural log of b plus mx. And the integral of x over 1 plus x squared is 1/2 natural log of 1 plus x squared. All integrals that we have encountered in one form or another before. Clearly, we're going to be looking at variations of these things. So let's take a look at variations, starting with this arctangent up here. What if it's not a 1 plus x squared? What if it's not 1 plus 1x squared? What if the constant and the coefficient are different? So let's take a look at that. So now our job is to look at variations of all these things. Now we're going to look at variations of the basic three integrals and see how we can incorporate some changes. Start with the basics and then add stuff to it. And we're going to start with the tangent, specifically something that will use the skill that we just learned, which is trigonometric substitution. So what if we have an integral of, instead of 1 plus x squared, let's suppose that we had something like 9 plus 25 x squared. Dx. The core thing here is this is 1 over 1 plus x squared. It's just that there's a 9 for the constant and a 25 for the coefficient. What we want to recognize, the first thing that we think of when we see this 1 over an x squared, 1 over a quadratic with complex zeros, this is going to be some kind of arctangent. That's what needs to occur to us first. This is going to be some kind of arctangent. We have a constant over a quadratic with complex zeros. That's going to lead to an arctangent. So let's see this in action. Let's start building the experience so that becomes a memory. We know that this is going to be a trigonometric substitution problem. Even though there's not a square root, we've got this a squared plus x squared business going on. And so that says we can do a trigonometric substitution. We've got to figure out what our substitution is going to be. And for that, I got to factor out the 25 to see what's actually going on here. What's a? So if I factor out the 25, that's going to leave a 9 over 25 plus x squared. So now I have a clear view. Factoring out the coefficient of x squared gives us a clear view of what a is. And so our x will be 3/5 tangent of theta. This means that dx is going to be 3/5 secant squared theta d theta. And the thing that we're going to use is 1 plus tangent squared is secant squared. So that's the thing that we're going to use. So let's go ahead and use all that. So we have to integrate. We have a 1 over 9 plus 25 times 3/5 tangent theta all squared. And then the dx is 3/5 secant squared theta to theta. So the thing that we expect to happen, the Pythagorean theorem, that has to show up, and that always shows up right after the substitution. So 9 plus 25 times 3/5 tangent theta squared is going to be 9 plus 25 times 9/25 tangent squared theta. And then the 25s cancel out. That's why we needed a 3/5 and not just a 3. And so this is going to be 9 times 1 plus tangent squared theta. And so this is going to be 9 secant squared theta. Notice that this is not under a square root. So we hit the unintended end of page cliffhanger. Let's simplify these. Let's first review what's going to happen. Notice I've got this secant squared in the green. That was from the dx. And in the denominator, I've got another secant squared. They're going to cancel out. So all we're going to have is a 9 times 3/5. So 27/5. Oh, wait, no, the 9's in the denominator. So one of the 3's will cancel out, and we'll end up with 1/15. I knew that sounded wrong when I said it. Still said it. So our simplified integral, I'm going to write all the details on the next page. In the denominator, we ended up with a 9 secant squared theta. In the numerator, we had a 3/5 secant squared theta d theta. I didn't give myself enough room to write the 3/5, so it had to get pulled out in front. So what happens is that the secants cancel out. The secant squareds cancel out, and so all we're integrating, see, 3 and the 9 cancel, is a 1/15 the integral of a 1 d theta. So the integral of 1 d theta is theta. Here's our antiderivative in g. Sorry, our antiderivative in theta, and we need to go back to our antiderivative in x. If we remember that x was 3/5 tangent theta, we can use this to solve for theta. If x is 3/5 tangent theta, then tangent theta is 5/3 x. And so theta is arctangent 5/3 x. So the integral of 1/15, the integral of 1 d theta is a 1/15 theta, and theta is arctangent of 5/3. And there's our antiderivative back in x. So the important thing that we want to notice is that we started off with a constant over a quadratic with complex zeros. That's going to lead us into arctangents. Constants over quadratic with complex zeros is arctangent. That's the first thing that we want to recognize. A constant over a quadratic with complex zeros is going to lead to an arctangent. We need to bump this up one more level. What if we had a linear function on top of this quadratic with complex zeros? So since we're dealing with polynomials and or rational functions, which means we're dealing with polynomials, we can just do this in different degrees. And so I started off with 0 degree over quadratic with complex zeros. So I'm going to push this up to 1 degree, first degree over a quadratic with complex zeros. So let's suppose that I wanted to integrate 7 plus 2x over 9 plus 25x squared to x. Rational function. We notice that this is different than the previous one. It's different than a constant over a quadratic with complex zeros, because we have a constant over a quadratic with complex zeros, and we also have this linear function over a quadratic with complex zeros. But the key thing that you want to notice here is that the denominator is quadratic with complex zeros. This is a mouthful, saying things like quadratic with complex zeros, but it's really important to say it this way and not say unfactorable, because it's not the unfactorableness of the denominator that makes us use arctangent, that leads to arctangents and natural logs. It's the complex zeros that's doing it to us. So we're going to start off with just a little bit of algebra. And we're going to use the distributive property. We're going to distribute to the two terms in the numerator the 9 plus 25x squared in the denominator. So we're going to start by making two integrals. So I'm going to have an integral of 7 over 9 plus 25x squared to x. And then I'm also going to have an integral of 2x over 9 plus 25x squared dx. We're going to use the distributive property to write two integrals. Specific distributive property I'm using is that multiplication distributes over addition. That means division distributes over addition as well. Now notice that that first term is the one that we just did. And the second term can be done with substitution. So 7 over 9 plus 25x squared, this is the one that we just did. So we started off with our constant over a quadratic with complex zeros, and our second term can just be done with substitution. So W is 9 and 25x squared. So dW is 50x to x. So a 1/50th dW is x to x. So now we have both of the terms. 7 over 9 plus 25x squared, that's just a multiple of what we had before. So that's going to be 7/15 arctangent of 5/3 x plus c. Oops, I don't want the plus c yet. That's just 7 times the one that we just did. Constant over a quadratic with complex zeros is going to lead to arctangents. And what we're noticing now is that a linear factor, a linear over a quadratic with complex zeros, is going to lead to natural logs. So we're going to have a 1/50th times 2, so 2/50ths or 125, plus 1/25th, the natural log of 9 plus 25 x squared plus c. And so that's our new thing. A linear over a quadratic with complex zeros gives us natural logs. So we're already looking at variations. We can see what's going to happen if we have a squared plus b squared x squared. We can see how in the arctangent where those constants are going to show up. So it looks like we're going to get an a and a b over here, and it looks like up here we're going to get a b over a. So 1 over ab and then b over a. This looks bad. Any questions? If it's starting to seem like this is a lot to remember, that's only because this is a lot to remember. And I'm asking you to remember all of it, all the time, in perfect detail. Think about all the songs you know the lyrics to. I'm not asking that much.
Hey, Professor, do you have any resources or like websites that you prefer over the textbook to practice these kinds of problems?
I think the best course of action is to look up trigonometric substitution problems on YouTube, because they'll write down the problem that they're about to do, then you attempt the problem, and then you watch someone do it right in front of you.
Got it.
And then you look for the variations. So there's a lot of places where you can look up a problem, but it doesn't have someone attached to it talking you through the solution. So that's one of the great things about YouTube, is that you can find a trigonometric substitution video. They're all over the place. And then you can pause the video, practice the problem, and actually watch someone do the problem that you just attempted.
Sounds good. Much appreciated.
That's my recommendation. Any questions? All right, so the first thing we have to learn to deal with is integrating a linear or a constant over a quadratic with complex zeros. I just went up 1 degree. After that would be a quadratic over a quadratic with complex zeros, or a cubic over a quadratic with complex zeros, but we don't have to deal with that. We've done all the calculus portion of things. If we have something like a quadratic or higher degree, so a polynomial of degree greater than 2, and the denominator is quadratic with complex zeros, then we just use algebra to get the numerator down to where it's linear or constants. Any questions? So here's the next step. What if it's degree higher than 2? So the denominator is still quadratic with complex zeros. And the numerator is a polynomial of degree 2 or greater. So what if the numerator, still we're keeping constant the quadratic, or we're keeping the same, the quadratic with complex zeros in the denominator, but what if the degree of the numerator is greater than 2? All right, so what if that happens? So what we're going to do is we're going to rewrite this so that we get a polynomial and then we separate out the fraction part. So what we're going to do is we're going to take something like 8/3, and we're going to write it as, oh, 8/3 is bad. That's a bad choice. Everything's going to be the same. Take something like 7/3, and we're going to write it as 2 1/3. This is what we're going to do. If the numerator is a polynomial of degree greater than 2, I know that 7 is a constant, but we're going to do the same thing. We're going to rewrite our improper fraction as a mixed number, and then we'll have some polynomial, and then we'll have a fraction where the denominator is a quadratic with complex zeros, the same one that we started with, but the numerator will be of degree less than 2. And we're going to do this, and we're going to get there the same way. We're going to go from a polynomial of degree greater than 2 over a quadratic with complex zeros. And we're going to rewrite it so that we get a polynomial that's going to be our whole number, plus a fraction where we still have the same quadratic with complex zeros, but now the numerator will be degree less than 2. We're going to go from an improper fraction to a mixed number. So the technique that we're going to use to go from the improper fraction to a mixed number is the same technique that we always use to go from an improper fraction to a mixed number. We just divide. So the process to go from an improper fraction to a mixed number is just to use division. So 3 goes into 7 2 times with 1 left over. So 7/3 is 2 1/3. We're going to use the same process, but it's just going to have polynomials in it. Any questions? So for example, let's take it out of the integration part. Let's take it out of the integration part. Let's suppose that we have a fraction that looks like 8 plus x squared over 1 plus x squared. The degree of the numerator is equal to that of the denominator. So we're going to use division. I'm going to take the 1 plus x squared. Well, I should write it in the normal order. And I'm going to divide that into x squared plus 8. We do the same thing, where here we said 3 goes into 7 2 times. What that means is that I can subtract 3 from 7 twice without going negative. I can subtract x squared from x squared once without going negative. So 1 times x squared is x squared plus 1, and then I subtract. X squared minus x squared, here I am subtracting x squared from x squared once without going negative. And then 8 minus 1 is 7. So I can rewrite this. Oh, well, that's fine. I can rewrite this polynomial as 1 plus 7 over 1 plus x squared. Now, the numerator of my quadratic with complex zeros is only constant. So if I wanted to integrate, let's say 8 plus, oh, I wanted a 5, that's right. If I wanted it, sorry, I'm just thinking because this came out differently than the one I had in mind. But it worked out just fine. If I wanted to integrate 8 plus x squared over 1 plus x squared, I would rewrite the integrand as 1 plus 7 over 1 plus x squared, because we know how to integrate that. So if I wanted to integrate 8 plus x squared over 1 plus x squared dx, there's no trick to it. It's just a simple trick. We hit it with the algebra stick. Now it's terms, and I can integrate 1. The integral of 1 is x, and the integral of 7 over 1 plus x squared. It's constant over quadratic with complex zeros. And that tells us it's going to be an arctangent, 7 arctangents of x plus c. Algebra to the rescue. Any questions? So we can now, we've covered a lot of ground. I'm going deliberately really fast through this. I don't know if deliberate is the right answer, but I deliberately drank coffee this morning, a lot of coffee this morning. So maybe that's, by the transitive property of deliberateness. But we've covered a lot of ground, but we do have a lot of ground to cover. We're trying to integrate all these rational functions. And we're starting off by dealing with a denominator that is quadratic with complex zeros. We can now deal with a denominator that is quadratic with complex zeros. So denominators that are quadratic with complex zeros, we've taken care of all of that. All we have to do now is practice. We have an answer for any rational function for which the denominator is quadratic with complex zeros. No matter what the numerator is doing. If the numerator is constant, then that gives us arctangents. If the numerator is linear, that gives us natural logs. If the numerator is of degree greater than 2, that means we use division to get to the mixed number form. Then we just have to integrate a polynomial, and then we'll have some arctangents and some natural logs. So we can deal with denominators that are quadratic with complex zeros. This leaves 2 open questions. Denominator is degree greater than 2. That's one thing that we have to deal with. And then what happens if the denominator is quadratic with real zeros? This will cover everything. Once we can deal with denominators that are quadratic with complex zeros and denominators that are quadratic with real zeros, that will allow us to progress with denominators of degree greater than 2. And once we get there, then we're done. The fun part is the next phase is just algebra. So this is going to be an algebra class for the next couple of days. Any questions? Comments? Snide remarks? That was a lot, but I get to do a lot because I record these things and put them up on the YouTube, so you can always just pause me later. That's why most of you just log in and just kind of like go finish your breakfast and stuff like that. Come back at 9. Or just actually, you don't have to even come back. I log you all off because I end the meeting. Because that's math school in 2020 and 2021. I hear we're doing this again in summer and in the fall. So I guess I'm really just putting the living in my living room. That's going to do it for today. I will see you all on tomorrow. Everybody have a great day, and thanks for playing.